Finding derivatives for exponential and logarithmic functions provide unique challenges. This sequence of two resources considers finding the derivative for these transcendental functions. Part 1 considers the derivative of exponential functions. First, we look at exponentials with the base e. Then, look at exponential functions with any constant base. Part 2 considers the derivative of logarithmic functions. We explore the derivative of the natural logarithm, then expand to find the derivative of logarithms with any base. We have the function f of x equal to e raised to the x power, and we want to find its derivative. Using the formal definition of the derivative, we have the limit as h approaches 0 of the quantity e raised to the power x plus h minus e raised to the x divided by h. We can perform some algebraic magic. A base raised to the power of a sum is the same thing as the product of the base raised to each part of the sum. So e raised to the power x plus h is equal to e raised to the x power multiplied by e raised to the h power. Factoring out the common term in the numerator, we have the limit as h approaches 0 of e raised to the power x multiplied by the quantity e raised to the power h minus 1 divided by h. Because the e to the x makes no mention of h, we can move that in front of the limit. We have e to the x multiplied by the limit as h approaches 0 of the quantity e raised to the power h minus 1 divided by h. But what happens when we actually take that limit? E to the 0 power is 1. So we have 1 minus 1 divided by 0. We have a situation where we have 0 divided by 0. But let's take a look at the graph for the function y equals the quantity e to the x minus 1 divided by x. This function clearly approaches 1 as we approach x equal to 0, both from the left and the right. So the limit as h approaches 0 of the quantity e to the h minus 1 divided by h is 1. So the derivative of e raised to the x is e raised to the x. But what happens if we differentiate exponential functions with other bases? Suppose we want to find the derivative of the function a raised to the power x, where a is any constant value other than 1. In order to find the derivative, we need to do some manipulation. Because they are inverse functions, we can raise e to the power of the natural logarithm of a raised to the power x without changing the problem. This is exactly the equivalent of subtracting a constant from both sides of the equal sign in order to solve a linear equation. We can further simplify the problem because the logarithm of a quantity to a power is equal to the power multiplied by the logarithm of the quantity. So we are left with e raised to the power of x multiplied by the natural logarithm of a. So the derivative with respect to x of a raised to the power x is equal to the derivative with respect to x of e raised to the power of x multiplied by the natural logarithm of a. This is a situation where we need to use the chain rule. We have e raised to a power where the power itself is a function of x. So our derivative will equal the derivative of e to a power multiplied by the derivative of that power. We saw earlier in the resource that e to a power is its own derivative. So we have e to the power of x multiplied by the natural log of a, multiplied by the derivative with respect to x of x multiplied by the natural logarithm of a. But the natural logarithm of a is just a constant. So the derivative with respect to x of x multiplied by the natural logarithm of a is just the natural logarithm of a. We have the derivative with respect to x of a raised to the power x is e to the power of x multiplied by the natural log of a multiplied by the natural logarithm of a. However, we recall that e to the power x multiplied by the natural log of a is equivalent to a raised to the power of x. So the derivative with respect to x of a raised to the power x is a to the x multiplied by the natural log of a.